Okay, so this is about significant digits. So when you record a measurement, this information is going to determine how many digits you put in your value. So when you type some numbers in the calculator to do some math, you get this really long decimal or number sometimes that fills up the whole screen on the calculator. We do not need all of those numbers when we are doing measurements. So these significant digits rules are going to help you with rounding your answer to be appropriate for your measurements. Sig figs are going to include all of the known digits. So when you take a measurement, you know certain values that are there, plus one estimated digit. So the last number that you write is always going to be the estimated digit. Depending on your instrument, it's going to depend on the place value of that estimated digit. The number of digits reported are going to indicate the precision of the measurement. So the more digits that you have, the more precise that measurement. If you are measuring with a centigram balance is measured to the 10th place, so you're going to estimate to the 100th place. If you are measuring with a 4-beam balance, then a 4-beam balance is measured to the 100th place, so you would estimate to the 1000th place. So based on the precision of your instrument is going to depend where your estimated digit falls in your place values for your measurement. So for example, 100.00 is going to be more precise than just 100. We have these extra zeros here. These extra zeros mean that they're measured. So this instrument measured to the 10th place, which means we are estimating in the 100th place. So it could be 100.01, it could be 100.02, it could be, a little off in that last place. But we know definitely that this instrument is measuring to the 10th place. We know that that is where our mass falls if we're measuring mass. This value down here, our last significant digit, is falling in the hundreds place. So that means that this is the estimated digit. So it could be 110, it could be 99. We're not really sure what's actually there. This one, we definitely know that it is 100. This one, it's going to be somewhere close to 100. So 100.00 is more precise than just 100. The more digits you have, the more precise your measurement. So rules for determining significant figures. If it is a non-zero digit, then it is significant. So 24.7, 2 is non-zero, 4 is non-zero, 7 is non-zero. So this answer or measurement has 3 significant digits. For now, this is a 0, so we're not going to count that guy. The 7, the 4, and the 3 are all non-zero, so this has 3 significant digits. 7, 1, 4, they are all non-zeros. They are not a 0, so they are significant. So that one has 3 significant digits. Doesn't matter where a non-zero digit falls in a measurement. If it's not a 0, 1 through 9, it's significant. If a 0 is between non-zero digits, then they are significant. So 7,004. We know the 7 and the 4 count. These two zeros are between two non-zero digits, so that means that this has 4 significant figures. 84.03. We know the 8, the 4, and the 3 are significant. This 0 falls between two non-zero digits, so this has 4 significant digits in the measurement. 2.705. The 2, the 7, and the 5 are non-zero. They are definitely significant. This 0 falls between two non-zero digits, so it is also significant. 4 sig figs. If you have a 0 at the very end of a number, and there is a decimal in that number, those zeros are significant. So 43.00. These two zeros are after a decimal. They are after non-zero digits. Therefore, they count. That's 4 sig figs. 1 is significant. 1 is significant. This 0 is between two non-zero digits. This 0 is at the end. There is a decimal here. There are non-zero digits in front of it. That means it is significant. This number also has 4 sig figs. 9.000. These zeros are at the end of the number. There is a decimal, which means that there is a non-zero digit here. That means that all of these digits are significant. This measurement has 4 sig figs. So, a digit is significant if it is non-zero, a 0 between two non-zero digits, or a 0 at the end of a number with a decimal. So there are non-zero digits at the beginning of the number. It is significant. 2 cases where a digit is not going to be significant. First one, if a 0 is at the beginning of a number, meaning they're starting that number. There's going to be decimals here because the only time a 0 starts a number is if it's less than 1. So these zeros do not count. The 7 and the 1 count. This guy has 2 significant digits. 0 at the beginning doesn't count. There's no non-zero digit here. Okay? This 0 doesn't count. It's not significant. The 4 and the 2 count. So we have 2 sig figs. All of these zeros are at the beginning of a number. There is not a non-zero digit here, so we cannot count these zeros as significant. We have a 2, a 3, and a 1. 3 sig figs. If there are zeros at the end of a number without a decimal, you just have 100, not 100.0, just 100, then those zeros are not significant. 300 meters. Decimal here? No. Zeros at the end? Don't count. This measurement has 1 sig fig. 7,000. Is there a decimal here? No. Zeros don't count. 1 sig fig. 272,100. Is there a decimal here? No. Zeros at the end don't count. This guy has 4 sig figs. So, we're only going to count a number as significant if it is a non-zero digit, if it is a 0 between two non-zero digits, or it is a 0 with a decimal after a non-zero digit. Okay? The 0 is falling after the non-zero digit, and there is a decimal in the measurement. Doing math with significant digits. So when you're adding and subtracting, you're going to round your measurement to the least specific place value. Right? Your answer cannot be more precise than any one of your measurements. So remember, the longer the number, the more precise the number is. Your answer cannot be longer than any one of your measurements. If we have 0.5497, the last significant digit is falling here in the tenths, hundredths, thousandths, 10,000ths place. For this value, our last significant digit is falling here. Ones, tenths, hundredths, thousandths. That means that this significant digit is in the least specific place value. This guy is more specific. This guy is more precise. So when we report our answer, here we have 3.1807. We cannot have this 7 here. Okay? We're going to take the 7, and you're going to have to round your value. We want our significant digit falling here in the tenths, hundredths, thousandths place. Behind the 0 is a 7, which means we're going to round the 0 up. 0 rounded up goes to a 1. This guy is going to drop off so that our answer is 3.181. When you're multiplying and dividing, you're going to round your answer so that your measurement has the least number of significant digits overall given in the problem. Look at each one of your measurements. Whoever has the least number of significant digits. It doesn't matter where the place value is, just in general. Whoever has the least number of sig figs, that's how many your answer has to have. Remember, your answer cannot be more precise than any one of your measurements. So here we have 3.71. This guy has 3 sig figs. And 4.987. This guy has 4 sig figs. Which one's smaller, 3 or 4? 3. So when we report our answer, we can only have 3 significant digits in our answer. These two multiplied together are 18.50177. We need 3 sig figs. So the 1, the 8, and the 5 are our 3 significant digits. We're going to look behind the 5. Behind the 5 is a 0. 0 means we're going to just kind of round it off, which means we're going to lose all of these guys. So our answer is going to be 18.5.